Alright, so we're now going to talk about binomial probability. And like I mentioned in the previous videos, binomial probability is a type of discrete distribution. But before we get into what it formally is, let's just start with a motivating question. Alright, so a basketball player, let's say, has, let's say, 0.90 free throw success rate. All right. If she shoots three or four times, let's say, then what is the chance that she makes four shots? All right. So to recap this, uh, every time she shoots a basket or she shoots a free throw, she has a 90% chance or 0.9 chance of making it in. So if she shoots four times, we're asking what's the chance that she makes. Sorry, that I wrote four, but I meant to say two shots, let's say. All right. So what is the chance then that she makes two of the shots? And so this is sort of reminiscent from the problem in the second chapter where we had someone randomly guessing uh, problems on a quiz for a multiple choice exam. And, obviously her chance of making a basket is much better than getting the answer correct if you're just guessing randomly. But, so let's go ahead and work this out maybe. So, I'm going to be going back and forth between this screen and another screen here. And so naively, you might say something like, all right, well, she has to make four shots, right? She has to make four shots, and then let's say two of them are successes, and two of them are misses. And what's the probability that that happens? Well, the chance of the first two being successes are 90% each, right? Because she has a 90% chance of making a shot. The second, the chance of the second two shots missing are 10% each because she has a 10% chance to miss. So the chance that she makes one shot, makes a second shot, misses the third shot, misses the fourth shot, the probability that that exact event transpires is the product, right, of all four of these things, which I'm going to simplify to um, 0.9 squared times 0.1 squared. All right. So is this the answer? Let's go back here and look at this probability here. It says, if she shoots four times, what is the probability that she makes, four shot or two shots? Sorry. And it doesn't anywhere here say that it has to be the first two shots, right? It's just that she makes a total of two shots. So here, she's made a total of two shots, but that's not the only thing that can happen, right? It's also possible that uh, maybe she hits, misses, success misses. Maybe she makes the first and the last shot. Maybe she makes the second shot and the third shot. Maybe she makes the second and the last shot. And then maybe she makes the last two shots, misses the first two. All right. Now, is that all of them? Is that all the different ways that she could have made shots or not made shots? Well, it does seem like it is. If you work out, right, all of the ones that where she makes the first shot, all of the ones where she doesn't make the first shot, makes the second shot, all of the ones where she misses the first two shots and makes the third shot, you can count out all of those possibilities. But there's an easier way to think about it. There's total of 4 shots that she's going to take. She's going to make 2 of them. So how many ways can we, sorry, how many ways can we pick 2 out of 4 objects? And that's 6, right? There are exactly 6 ways. I'm going to go ahead and make it clear that that's not a 14. How many ways are there to pick 2 out of 4 objects? It's 6, right? We can review that this is 4 factorial over 2 factorial times 2 factorial, or you can use your favorite piece of technology to work that out. But either way, when we do the arithmetic here, we'll get 6 different ways that can happen. And there are, what, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right? Different things listed here. Now, when I go through these other 5 cases, right, we worked out the first case, right? It's 0.9, 0.9, 0.1, 0.1. If I go to the second case, it's 0.9, miss 0.1, 0.9, 0.1, right? And then when I go to the third case, it's 0.9, 0.9, 0.1, 0.1. And do you see what's going to happen for the others as well? In every one of these 6 cases, she makes 2 shots, misses 2 shots. So there will be 2.9s and there will be 2.1s, right? So in this case, it's 0.9, 0.9, 0.1, 0.1. Here we have the 0.9s here and the 0.1s here and here. And then finally we have the 0.9s at the end. And then the misses up front, 0.1, 0.1, right? So all of these possibilities end up with two successes and 2 misses, right? And there's 6 of them. So the probability that this exact thing happens then turns out to be, out of the 4 shots that she takes, she's going to make 2 of them, right? And then given some shot, say, all right, to make the 2 shots, there's a 90% chance each of making them, and then she does it twice. So the chance of that happening per one of these 6 choices is 0.9 squared. And then out of the remaining 2 shots, she misses them. That's a 0.1 chance. And sorry, there's 2 of those, right, that she has to contend with. Okay. Now, Let's generalize this, shall we? Um, what happens if instead of shooting 4 times, she shoots n times? Everything else is the same, except now instead of taking 4 shots, she's going to take n shots. Well, instead of things of length 4 here, we'll end up with a whole bunch of things of length n, depending on what n is. But the bottom line is, still, out of the n shots that she takes, we still have to pick 2 of them, right, to make. So instead of a 4 there, we're going to get an n there. She's still going to make 2 shots, so we still have 0.9 squared, right? But now this 0.1, that's going to be to the, sorry, let me move it over a little bit. The n minus 2, right? Because let's say n were 5, then she makes 2 shots. She has to miss 3, right? 5 minus 2 is 3. If she takes 10 shots and she makes 2 of them, then she has to make 8. So if she makes n shots and she makes 2 of them, then she has to miss n minus 2 of them. Well, what if she makes more than 2 shots, or less than 2 shots, or something not 2 shots? What if we're asking for the probability to make k shots? Well, in that case, I'm not picking 2 anymore, right, out of n. I'm picking k out of n shots to be successful. And then this 90%, instead of just 2 of them being successes, k of them are successes. And then instead of 2 of them being, or n minus 2 of them being failures, n minus k of them are failures, right? And so this would be the formula as listed here for if she has a 90% chance free throw success rate and she shoots n times and she makes k shots. Now, the one last thing we can generalize here is instead of a 90% success rate, she could have any possible success rate. She could have a 100% success rate. She could have a 0% success rate. She could have any number of successes that we can think of. And so what's different here, instead of the 0.9, we would just have p, right? Just some number, some probability for success, k times. And then 10% was the chance of failing. And to generalize, if her chance of succeeding is p, then the chance of her failing is 1 minus p. And then the last thing we can generalize is, of course, like the whole basketball thing is just a contrivance, right? Just to make up some sort of real world example. But we really could replace that with just about any scenario, right? Where you have a number of attempts to do something and there's some probability of success associated to that. All right. So if we were to go ahead and write out what this means more generally, this is actually kind of a wordy statement, so I'm not going to write it here with my terrible handwriting. Instead, I'm going to go ahead and pull up the relevant the relevant description from the text about the binomial distribution, and you can see this on page 147. And so, suppose the probability of a single trial being a success is p, right? And we want to compare that to, in this case, a basketball player's 90% or P chance of succeeding, right? So each trial has a single success. Then the probability of observing exactly k successes in n independent trials is given by n choose k, p to the k, 1 minus p to the n minus k, right? And that's exactly what we have written here in red, right? And then they just rewrite the n and k in the language factorials if you care about that. It's not a big deal if you do. And so this is a general formula for computing binomial probabilities. And so, just as a reminder, whenever whenever you have a formula of some sort that, working things out in it's just a matter of just plugging in some numbers, um, that's always a mechanical process. And whenever you have a mechanical process, it's probably best use of our time to allow a machine to do it for us. So, in our example here, we have uh, a basketball player who's going to take 4 chances and whose probability of success on each shot is 90%, right? So there are 5 possible outcomes, right? When she takes these 4 shots, she could miss them all. She could get 1 shot basket in, 2 baskets in, 3 baskets in, and 4 baskets in. And so we can see here in this particular case that the chance of her making only 2 baskets is pretty small, and that makes sense, right? She has a 90% free throw rate, right? And if you have a 90% free throw rate, you don't expect someone like that to miss half their shots, right? You expect them to make almost all their shots, especially if you're only making 4 of them. So, right, all four going in is the most likely event, right? It's not guaranteed though. Since she does have a non-zero chance of missing, there are non-zero probabilities listed here. Now, this gives us a probability distribution, doesn't it? So, you could ask the same question we always ask in cases like this, which is, all right, you have all of these, you have all these possible outcomes. So 0 baskets, 1 basket, 2 baskets, 3 baskets, 4 baskets, right? And they all have these probabilities associated with them. So we have a very small chance of missing all of them. Again, she has a 90% chance of making a basket in. So missing all 4 is really unlikely, right? There is some chance that she only makes 1 in, some chance 0.486 that she makes 2 in, making 3 in, 0.2916, and then making all 4 in 0.6561. All right. And of course, whenever you have something like this, um, you can compute an average outcome. What's the average expected number of baskets, and the variance in standard deviation. How widely varied is that? Uh, is that the number of baskets that you expect her to make? But if we look back at this distribution, there's pretty much only two things controlling this distribution here. And those two things are the number of baskets or the number of shots that she's going to take, right? And that will tell you what the possible outcomes are. And P, the probability that those shots are successful, right? And so only two parameters determine everything about this distribution. And therefore, it's sensible to think that only two parameters are necessary to determine the expected value, the variance, and standard deviation. So I'm going to go ahead and pull back up this box here. And we have here the average value, or the expected value is NP. The variance is NP1 minus P. And the standard deviation is square root NP1 minus P. Now, these latter two, I'm not going to go into a lot of detail on. There's a good reason for why this is the variance and standard deviation, but it's a little esoteric. If you want to think more deeply about why, say, maybe the variance is NP1 minus P, you should think about the fact that, you should think about the fact that a single basket has a distribution that's something like, if she just shoots one shot, she can make 0 or 1 of them. And those are the probabilities. And what X is adding this random variable to itself 4 times. So this thing has some sort of variance, and then we know from chapter 2 how to add together random variables and what those variances are. But maybe more straightforward is the mean being NP here. And so, if she shoots 4 baskets, what's the average number of baskets that she's likely to make? Well, we expect her to make 90% of the shots, right? So if she shoots 4 times, then on average, wouldn't she make 90% of the 4? So I'm willing to bet if you took these numbers here and computed the expected value of this distribution, so 0 times this, plus 1 times that, plus 2 times that, plus 3 times that, plus 4 times that, you will end up with 3.6, right? 90% of 4. And you think about it, if you shot 10 shot baskets, you expect her to make 9. If she shot 100 baskets, you expect her to make 90. If she shot 1,000, you expect her to make 900, and so on, right? So 90% is exactly what we think it should be. And so as part of this computation here, we do in fact see that the mean of this distribution is NP, which is 3.6. And then the variance and standard deviation are computed here as well. All right, so one final note, computations about binomial probabilities get pretty difficult and annoying as n grows in number. And so one thing I wanted to note is that, right, if you have a binomial distribution whose parameters are n and p, this thing has mean equal to np and standard deviation equal to oof, root NP 1 minus P. Right? What I'm about to demonstrate is that as n gets large, then this distribution is approximatable by a normal distribution whose mean is NP and whose standard deviation is the standard deviation. And the best way I think to make this look, to make this convincing, is to simulate it with a demonstration here. So what I have here is a probability distribution 0.5, 0.5. And so what this is it's a, let's say, a coin who has a 50% chance of coming up a 0 and 50% chance coming up a 1. And if I do this 1,000 times, what are the outcomes of that? And so we can see in this example here that there's 493 zeros and 507 ones, which totals to 1,000, right? And so they're pretty close, 50-50, right? Now, if I flip 2 coins, right, then and add the results together, we can think of the 0 and 1 as maybe the number of heads, right? So if I flip 2 coins and I add them together, the possible outcomes are no heads, 1 head, or 2 heads. And now if I do that 1,000 times, what we get is, all right, some number of 0 heads, some number of 1 heads, some number of 2 heads, right? If I flip it 3 times, then the possible outcomes are 0, 1, 2, and 3 heads, right? And they range about 149 to 351 or so. But look what happens as I increasingly bump up the number of coins that I flip. So here I'm flipping 10 coins. And what we get here are the outcomes from 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, 7 heads, 8 heads. Sorry, not quite. This is 1. The zeros and tens are very small here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Well, I flip 30 coins. Then I get a distribution that looks something like this, right? And doesn't this start to look fairly normal? And so if I were to flip 100 coins, right, we get a distribution that almost looks exactly normal, doesn't it? And what if let's go back down to say 1, but instead we'll go with our basketball player. If she shoots 1 shot, she overwhelmingly likely is going to make 1 shot, and there's a some but small chance that she doesn't make it, right? If she shoots, say, 4 times, which was our example, right, we got the distribution that we more or less saw from Desmos, where she's still most likely to get 4 shots than she would be to get 1 or 0 shots, right? Neither of those are very likely. But what if she shot 50 times? Well, now the mean is all the way out here. If she shoots 50 times, then 45 is the expected value of the outcome, and that's right about the peak, right, between 40 and 50. here? What if she shot 500 times? Take this a while, but yeah, we get a we get a very normal looking distribution right here, right? Again, 450 is the expected value, and that's the peak of this curve. We really wouldn't expect someone who has a 90% chance of success to shoot 100 or 500 shots and only get 200 or 300 shots, right? And so, uh, hold on. I could ask myself, for example, if I flip 100 coins, what is the probability oops, I get between 65 and 100 heads? Sorry, let me pull that back up. So if I flip 100 coins, what's the probability I get between 65 and 100 heads? And so this probability is estimatable by a normal curve whose mean is 50, right? On the expected value of the number of heads, if I flip 100 coins, is 50, and whose standard deviation is the square root of 1/2 times 1/2 times 100. And not that anyone's keeping score, but that's N55. And so we could estimate the probability that you would get between 60 and 100 heads by, or 65 and 100 heads by going to a normal curve whose parameters are 50 and 5 and go, all right, what's the probability you get between 65 and 100 heads? And the probability, as we see here, is extremely small. It's less than 1%. It's 0.135%, right? And if we want to find the analogous thing here, if I go 50, 50, 100, right, here we have a normal curve with mean 50 and standard deviation 5, and 65 is dead center. 65 is right about here. So what percentage of this curve is to the right of this point here? Almost none of it, right? So, I mean, 0.135% is about right. And so this is good for us because there's a lot of things practically that behave like the binomial distribution. And so if you, for an example, outside of the things we're talking about, let's say if you're a politician and you're trying to figure out, how people are going to vote, then people either vote for you or not vote for you, right? And so that gives you a sort of two-tiered system or two outcome system. And that's the kind of thing that binomial probabilities try to model, right? Given some trial, there's either a success or not. And so what I want to close off with is, and this is very important, is the conditions for a probability to be binomial. The first condition is that trials are independent, right? So in all of our examples, the outcomes of certain trials didn't affect the outcomes of other trials, right? Like if you're going to shoot baskets, you're not going to hit them all or miss them all, right? Each one is its own thing. The number of trials n is fixed, so this is not a case where you keep shooting baskets until you miss one or something. We're told up front how many coins to flip, how many shots to make. The trial outcomes can be classified as success or failure, right? You get heads, you make a basket, you get a vote, whatever it is you want to call that. And the probability is the same for each trial. And so this might make the basket analogy a little bit not exactly accurate, especially if you're going to shoot 500 shots. You're probably pretty tired by around 450 shots or so. But for small n, this is a pretty reasonable assumption to make, right? That this p is fixed. And so these are all things you need to verify before you can go ahead and assume that your probability is binomial. All right, so hopefully that helps. This basically closes out chapter 3. And so in the next video, we're going to start making predictions about the world. All right, talk to you then.